everyone. My name is Lenworth Thomas, and I am from the University of Florida. And today I'll be presenting the novel IMU-Compensated MEMS LiDAR scanning for mobile robotic platforms. So here's an overview of the things we're going to talk about today, and we're going to start off with an introduction to myself. So a little bit about me. I am, like I said, Lenworth Thomas, and I study mechanical engineering at the University of Florida. I'm originally from Orlando, Florida, and I plan to pursue a PhD in robotics and autonomous systems. So I'll be applying this fall, so that's going to be an interesting time. And then I'm a huge gardening enthusiast, so if you want to talk plants, hit me up. So some background information before we get started. Before we dive into the details of the project, I wanted to explain some important terminology. So first we're going to start with MEMS. So this stands for micro electromechanical systems. And this is essentially a really tiny circuit that has some kind of mechanism on it. So for us, we're actually we made a mirror that can modulate the direction of laser pulses. So I'll talk a little bit about that later. LiDAR is light detection and ranging, and we can use this to shoot a laser in one spot and then wait to see how long it takes to come back, and that essentially gives us the distance of a certain point. And then if we rotate that laser, we can get the distances of multiple points around us. And lastly, IMU is inertial measurement unit, and we can use this to get acceleration, velocity, and orientation of your certain point that you want to measure. So before I get into what our project is, I want to talk about where we started and how we got to that project. So we started out with a MEMS-based actuated mirror. So it's a MEMS circuit with an actuated mirror with a piezoelectric material that allows it to actuate in different directions, in the X and Y directions. Because it's so small, it uses barely any power compared to the spinning opponents in LiDAR, the ones that spin like I talked about earlier. So we created this technology, and we were thinking, how can we apply this technology to different things? So when I came into the lab, we started working on this project called the low power LiDAR. And this entire system runs off of a 9-volt battery, and we wanted to really emphasize how low power this system can be. So we were able to create a point cloud and even display it on the OLED on a display, all running off of that same 9-volt battery. So that was that. And so once we finished this, we were like, I wonder how we can apply this to another problem. So we were thinking that this could be applied to maybe a moving platform, so maybe a robot or a drone. So that's what we're going to be talking about today. So more about details about what the actual project is. So here's a general overview. So we're essentially separating the optics, laser, and MEMS mirror from the electronics. So we're taking the optics side of things and making that movable, and keeping the electronics at a fixed station. And we're using the laser data points to make a point cloud like we did in the last project, but we're able to actively modify that point cloud based on the IMU data that we have. And this allows for environment scanning for robotic insects and small drones. So a little bit more about the software. We're essentially, like I said, using the MEMS mirror and LiDAR data points, but we're inputting this into a MATLAB script to create a point cloud. So once the LiDAR shoots a point and waits to see how long it takes to come back, we then corroborate that with the MEMS mirror angle, and then we're able to plot that data as an actual graph to see the actual object that we're scanning. So here we have a paper cross that we scanned, and you can see the point clouds there. So a huge part of our project is IMU modulation. So using the IMU data gives us a lot of really new abilities compared to other projects. So we're able to stabilize the point cloud. So while the drone is moving or the platform is moving, we can obtain a constant point cloud regardless of the motion. Kind of how when you're recording a video on your phone, everything's kind of stable and in one orientation. So that's exactly what we want to do with our project. And also another thing it allows you to do is to keep the MEMS mirror stable regardless of where the platform is rotating. So an example of that is this drone here. You can see even though it moves back and forth, the camera stays somewhat stable. So that's essentially what we're trying to do, but with the actual mirror itself. Now on to the hardware part, my favorite part because I'm mechanical. This is an overview of our platform. So the major aspect of this project is our mobile platform and the software that goes through it, but this is the hardware part of it. So we're using a laser with fiber optic, and the fiber optic allows us to move very far from the electronics without any latency issues because of how effective fiber optic is. And the other components we're using is MEMS mirror, like I talked about earlier, and then I created a custom 3D printed mount for all of these components that can be mounted onto the drone. We also made another configuration that is static that I'm going to be talking about in a few slides. And then it also accounts for an adjustable aperture iris that we can use to focus the laser beam on the MEMS mirror. And then we're going to be using a DJI teledrone to carry the platform. And you can see these two prongs here that snaps onto the drone and allows it to stay fixed on the drone while it moves around. So here's some more data about the hardware. So on the left you can see some of the components of our CAD, and I designed this structure specifically to be really light and small, but also to fit on a multitude of different platforms. But I designed it to fit on the DJI teledrone. The entire thing is just about 9 centimeters and weighs 7 grams, so it's actually really light stuff. So the applications of this are really broad. Now that we've talked about the technology that lets this project work, let's talk about how everything integrates together. So the right side is the fixed hardware, and that stays tethered to the movable scanning platform, and this movable scanning platform can be moved by hand or can be moved with a robotic platform. You can see the laser shoots out its laser pulses, and that goes to the MEMS mirror, which reflects it, and then it shoots it off to a point of interest. And so that MEMS mirror can change angle in both the X and Y directions and creates that point cloud that we want. So all those data points go back to the fixed hardware, and through the software it makes the point cloud. So now that we have a general understanding of what we're doing, so here's just some pictures from our static test. This is the one we're in progress in doing right now. So we modified the platform design slightly so that it could be used in a stable environment. Everything is fixed, and like I said, we're working on optimizing the algorithm, and you can see everything. This is how we scanned it with the point cloud right there. And a really exciting thing that we're going to do is obstacle detection. So we're going to use the LiDAR to predict a collision. So once an object is detected, we can either wait for the object to move, or we can go around the object depending on its size. So I'm going to show you what that would look like. So for the first approach, if we were to wait for the object to move, it would fly up to the object moves, and then the drone will keep going. Or the second approach would be to go up to the object, scan the object, and see how big the object is, and then determine how big of a course correction it needs to make. So that's the next experiment. Then the last experiment is the RoboBee simulation. So we're actually using the RoboBee data to simulate what that motion would look like to create a stable point cloud and show that our system can account for vibrations. So we would start off with just a normal rectangular course, something like this, and then when we switch to RoboBee mode, it will be a little bit more erratic, and we can show that the IMU data is actually accounting for the motion and making a stable point cloud. So some use cases of our project is, like I said, robotic insects is a huge one, small UAVs as well, and then autonomous cars, because in vehicles there's a lot of vibrations, and vibrations are something that we can really account for by using the IMU, because kind of same example, like if it moves back and forth, we can kind of account for that by modulating our MEMS mirror. So next steps for this project, like I said earlier, we are finishing up experiment 1, and next we would just continue through experiment 2 and experiment 3. Here's my references. And thank you guys so much for listening to my presentation. If you have any questions, feel free to let me know in the Zoom call. And special thanks to these people right here. And yeah, thank you guys so much.